He is an extremely bright individual. I'll let him describe his own background, but he's going to here today to actually talk about topic modeling in a very, very interesting way. So with all that being said, I'll let him introduce himself. So
thanks,
Josh,
John.
go ahead.
So, thank y'all. John mentioned I'd be talking about topic modeling. That will be a smidgen of what I'll be talking about. There will be a lot of other exciting things that I'll bring up, topic modeling being one of them. So, I'm Josh Gieringer. I work as a data scientist at Digital Reasoning. I went to Belmont University, grew up in Little Rock, Arkansas, escaped to Belmont, been in Nashville since. After graduating with a degree with computer science and a minor in biology, I wanted to do something with NLP, also wanted to do something with biology, medical research, and ended up getting my first career at Vanderbilt with their Population Health Informatics department. And so there I worked on NLP tools. A lot of them were very rules-based, but it was a really good introduction for me and a good experience for me to just jump down some holes, dig myself out, take notes along the way. And lo and behold, I got a job at Digital Reasoning, getting to use those tools that I once worked on building. So my life has changed a bit. I like to think it's been way more exciting as a data scientist than grinding away, finding out why this part of speech tagger isn't working. So that's kind of been my life. At Digital Reasoning, I help out with healthcare. So I'm going to healthcare companies, hearing what keeps them up at night. At Digital Reasoning, our bread and butter is text classification for most of our projects. So I'm looking at radiologist notes, physician notes, you name it, denial letters, whatever a healthcare company wants me to look at to help them perform more efficiently and also save some lives and save some money while at it. So today I want to talk about one of the very first steps of what I do as a data scientist, and that's exploratory data analysis, which topic modeling is a part of. I'm seeing John kick himself back there. And let's go ahead and get into it. So there are 3 stages to EDA, and I will get into them right now. The first stage, we have a lot of pictures today, folks. This is going to be a lot of fun. First stage, a client comes to me and says, we have this data. We have this data, and we don't really know, we have an idea of what's in it, but we also have this desire to do some modeling and create some solution towards this problem. So a problem I can tell you all about is we've worked with HCA to read pathology notes, to model on pathology notes to detect cancer. And this is to encourage quick follow-up and make sure that patients are followed up with within 48 hours of finding out that they have cancer, to make sure that they're within the hospital and just that they're taken care of. When we first started this project, they said, okay, we have all these pathology notes. What's in them? We have all this untapped knowledge. We have data scientists that have worked on structured data, looking at trends of timelines, of vitals, of, you name it. Anything with a number already attached to it. But as I said, with our bread and butter being text, they came to us and we met their expectations. So we took these pathology reports and we just crunched a few numbers, and we found out that the data that they gave us, we could do something with it. So this is kind of what this is like. They hand us a sample of data, so a small little piece of data. They want to know, is it worth it? Is it worth my time? Is this data worth their time? Is it golden, or is it more of that? So number 2, second stage of EDA, we've been working with subject matter experts. I've been sitting with them. They've been labeling data. This is after we've gotten the thumbs up on let's use this data. And we want to start modeling. So let's say we're doing some classification tasks. We have our labels, we're ready to start fitting, but the EDA portion of that, to know if we're modeling, the left kind of modeling, not the right kind of modeling, is going to work. So with those labels, are the classes balanced? Are they imbalanced? Do we need to go in on these features and be able to explore, with this class imbalance, how do we then treat these features? Do we weight them differently? And so forth. So all of this goes into the EDA portion. Number 3, we've built a model. We're so stoked about this model, but now we want to know if it generalized to our initial test set and it's running at this client. But say a new client comes from out of this world. Yeah. And we want to know, how does our model generalize to this data? Not only has it not been seen before, but we're unsure if the features align, what our model's going to think about it, and we might not even have some labels to just run and get cross-val score and see what happens. So what are some things that we can do in the meantime while we wait on labels to truly score this unknown data? So this is kind of like cracking open an engine or a model and looking at what features lie within the data, and how these features and the feature presence of this data compares to our data that we trained on and tested on. Make sense? We got to make sure that we can scale. So that's the thing. But today I'm going to talk about the first stage of EDA, and that's when a client comes to me and says, hey, I've got this data. I would love for you to look at it. I want you to let me know if this is worth my time, if it's worth your time, if we can get something going. So as a data scientist, have y'all seen these? 6th grade? Taking y'all back? Anyone? Cool. The scientific method. We're still using it daily, and we're using it to really just come up with questions. We have the purpose, state the problem. Usually a client's coming, man, we really want to detect cancer in these pathology reports. All right, let's research about this topic. Let's hypothesize that the data is good enough. Let's experiment on this data. Let's analyze it, and let's conclude. That's day in, day out. That's the grind.
Do you guys have this chart on your wall?
Yes, it is everywhere at Digital Reasoning. Yeah. So the first thing, again, we want to research. So we're researching, we have this data, we're reading, we're making observations. I'm not even crunching numbers right now. When someone gives me some data, I am loading it up. I'm not printing it out because PHI and stuff, but that's best practice. I'm reading it, I'm taking note as though I'm trying to become a subject matter expert. That's what the research is about. That's me trying to answer some of these questions myself by reading the literature, but then coming up with questions and going back to the client and say, hey, I noted this, and this. I'm seeing a lot of misspellings of cancerous. Does this happen often? And these subject matter experts, these are people that are doing what I'm doing for just like a week. They're doing this every day. And I'm trying to make their job a bit easier. And so they're coming to me and saying, yes, this data set is representative of what I see every day. Yes, this is, doctors misspell a lot of things. Stuff like that. So it helps me take notes for if the data is worth it, that when I get into modeling, I know the nooks and crannies, the hiccups, and the praises, the shortcuts, you name it. So I'm trying to find, does anyone know what movie this is?
Spirited Away.
Yeah, thank you. So we're trying to find out, we're trying to conclude. Actually, this is the step on hypothesizing. We're hypothesizing that the data is good. And if the data isn't good, it could eat us up if we try and go into modeling with it. Okay, so we've done observing, we've done the research, we've gone back to them, we've hypothesized with them, and now we're ready to get into the meat of it and actually start doing some experimentation. Yeah, this is awful, right?
Hopefully it's well done.
Yeah, it's looking a lot better than well done. So, text. We have this huge sea of documents that if I throw it at a computer, it doesn't really know what to do with it. It's just like a confused Wall-E is what I see. So this is what I imagine is what text would look like going into a computer. How do I turn it into something like Legos? You get it? Sea of plastic, Legos. All these Legos have different attributes. They have different sizes. They have different colors. And all these things can help us build what we are wanting to build. They can help us build something better than what we wanted to build. It's all in the information. So how do we go from here to here? You have to have the right tools. Cool. So this is, I'm going to take away from all the pictures right quick and just give a quick example. This is something that blew my mind when I first started working with text data, is how do I get text, like text from documents and so forth, as a feature vector? People kept telling me it's a feature vector, and we want the features. And what's a feature when we're talking about text? So here I have two sentences. Donuts are my favorite food. It's a fact. My favorite part about EDA is when it is over. That's kind of a fact. I have a lot of fun, but I feel like I could do EDA forever. So let's say we have these two sentences in a list. This is our feature vector. That's all it is. If someone had told me that like 2 years ago, I feel like I would be at Google or something right now. But so here I am. So we still have document 1 and document 2. And what we're doing is, it's just the counts. It's how many times this word, feature, shows up. That's all there is to it. We can do some extra stuff, such as say, let's one-hot encode it, where if it's present, then it's just going to be 1. If that feature or word isn't present, then it's going to be a 0. It's as simple as that. But then we notice, man, if we start loading a lot of these documents up, we have a lot of features. When people are doing machine learning and stuff on structured data sets, they're doing stuff such as feature engineering. We had a session today where we were looking at some structured data, and it was wonderful. But when we're looking at structured data, we're going up to like 100 at most. We can still find some correlation in there, and it's pretty easy to look at those one at a time. With text data, as words keep coming up, and we have such a big nomenclature as the human race, this feature space grows, and it gets really big. I remember my first project, I did vectorization, that's what we just did here, on character level, and my feature set became like 80,000. There's no way I'm gonna really find some good correlation without overfitting with that kind of feature set. So, what are some things that we can do? Stop words. We can look at words that really don't mean anything to us. When I'm going to a subject matter expert, when I've done some analysis on these features, I sometimes bring a list to them and say, hey, how do these features work out with you? Do these ring any bells for you? And sometimes they're like, no, or I haven't thought about that. And they learn something new. Or I learned something new. But a lot of this is we're reducing the noise. We're reducing things that show up in a lot of documents that really aren't going to help us in our modeling efforts later. Furthermore, what if, okay, stop words, I can think of like 100, maybe 200 words. There's still going to be 20,000 or so features if I'm looking at a big corpus. So what are some other things I can do? I can look at frequency tuning or frequency filtering. So let's see, favorite shows up in all the documents. We can cut that out. We can say if a term is showing up this many times, or it fits in the top 5% of common terms, throw them out, because those are just way too common for me to find anything out about you. Or we can say, man, there's a lot of rare terms in here that a model might try and really focus on because that's some hope that it's holding on to. or it's just something that's just extra noise. So we can say, hey, if a term only shows up 9 times, get rid of it. So we can have these kind of frequency filterings. And there's a lot of other ways that we can do this, but these are some really good starters on getting into this exploratory data analysis. So you saw that we had the feature vector. Now we have our feature set of numbers. Now we can do all these equations. I'm not going to try them, but we can do all the math on these features. We can find out how distant points are from one another. We can find out, what terms are happening the most, what columns are most prevalent, you name it. We can do some really cool stuff. And that's where things really get exciting. The meat, I remember. We can also do some fun plots. So, y'all done box and whisker plots before? It was painful. It was really good. So box and whisker plots where we can look at distributions. How often are these words showing up? How long? What's the size of documents? Median, average. What are the outliers? So this can further drive our questions. We can look at what's sticking out of the distributions and read a sample of those and come up with some more questions to go back and say, man, here's another live example. We started getting a lot of outlying documents that had a lot of addendums on them. Addendums are people going back to the report, pathology report, radiology report, and saying, following up on this and writing some new notes. They're rethinking what's happening. I'm like, okay, we have all this. What do you want us to do with this? Would you rather us focus on these addendums? Would you rather us throw them out and focus on the regular report? How do you want it? So it's driving questions. It's helping us keep in a tight-knit relationship with our client. And it's helping us understand how to deal with this data when these things come along. Who doesn't love a word cloud? Our clients love them. So we're going to make those, of course. These are just, let's grab a count of the top terms and then just throw them in some cloud and they come out and it looks really cool. It doesn't really help me, but I've seen people just really start nodding their heads when they look at word clouds. I'm like, all right, they get it. They get it. I don't get it, but they get it. Another thing we can do now that we have those feature vectors, we can do what John was talking about earlier, topic modeling. So topic modeling is like what we're doing right here. We're feeding all these documents into this algorithm. It's unsupervised, which means we're not saying, hey, here are our labels, is the data. Try and find patterns that match to be able to output these types of labels. Unsupervised means it's on its own, it's finding these patterns, it's finding correlations, and with topic modeling, it's going to tell us themes that exist within these documents. And so these themes are coming out of the words that are showing up together. They're also coming in the documents, and there's a couple of algorithms that really go through that. And I have a present for y'all when I finish all these pictures. But it's going to talk about what I know towards topic modeling, LDA specifically, latent Dirichlet allocation. Very fun. Go Bayesians. So that's that. Once we have some topics, we can kind of understand what kind of words are showing up closely together, what kind of documents are clustering together. We can also just understand really what terms have such high probabilities towards these topics as well. They might even come in handy on helping us find new data. If, say, new data comes in, or if we have a class imbalance and we really want to find that that minority class, topic modeling can help recommend some of those samples. So it can help us out. Also, t-SNE plots. These are one of my most favorite things to do, and they've never really helped anyone that I've shown. But I think they're so cool, and that's a part of my gift to y'all today as well. So in these plots, what t-SNE does is it's we have these huge feature vectors. When I say huge, I mean the length of them, how many features exist. So earlier I was saying there's like 5,000, 20,000 features. Let's say we trim them down. There's still not a good way to visualize these. And so what TSNE does, it's by a guy named Lars Vanderbilt, cool name. He wrote this in 2009, and basically it's doing kind of like nearest neighbors, but finding out these nearest neighbors. So here we have like red, pink, green, and so these are our local neighborhoods. And what TSNE is doing is it's preserving these neighborhoods, these distances, and furthermore the probability that this data point is a neighbor to this data point. So I call it a distance probability. We're trying to maintain those distance probabilities from a high dimensional meaning all of those words. We have a lot of features, a lot of dimensions, to a 2-dimension plane that we can actually get an idea. We can visualize, and TSNE, people will always say, this is crap. This doesn't show what these documents really do. And you're right, like I've plotted where like a logistic regression line would be, and then where my test and validation set is nowhere close to right. But what it does show is the local neighborhoods. It's showing me what pieces of data are grouping together. And when I know those groups, I have a better idea of that data. And so I had a plot for y'all. This is all y'all get tonight. I had a plot for y'all and it broke my computer. So when you are doing TSNE, it can be a bear to run, especially when you're trying to visualize 30,000 points. So my comment on that, take a sample and start with a sample and grow your data points, because it can also take a while. So at the end, actually I want to read this really quickly. This is pretty good. But so I'm going back to why am I doing all this? It's so I can come back to the client and say, hey, your data is worth it, or hey, I'm not so sure about your data. I either need more time, I either need more data, or man, I am too busy to worry about this, and let's talk in a couple months. So that's basically the conclusion towards our scientific method. We made observations, we performed some research, we asked questions, we hypothesized, we were really hoping that the data would be good, and we did experiments on it, we found distributions, we counted things, we plotted things, we really feel good about this data, and then we're able to come back to a client and say, yeah, let's do this, let's move on to the next step. So that's how things work. And so this is my last slide, just classic T.S. Eliot. Like I said earlier, I don't think I could ever be done with EDA. I've had teammates over at Digital Reasoning pull me off of like tickets that I was doing for EDA because I was spending way too much time. I was having way too much fun. That was really it. Because there's always something I can go in. So like tonight, we're talking about counting things. There's features. We were really looking at some just basic stuff. I think the stuff that I talked about tonight it's general across a lot of playing fields. But when we start getting into more types of data, like healthcare data versus something we also work on, financial data, there's kind of differences of subjects. So one of my favorite libraries is called Spacey, and it's an NLP library, and I love doing counts for like named entity recognition, seeing whose names are showing up a lot. If you get the Enron data set, you'll see a lot of fantasy football talk, and so that's a lot of fun. And I can't really work with the Spacey engine over on healthcare data because it's not telling me that this is a disease or this is a medication. For that, I would move over to something like UEMA, which is one of Apache's frameworks, and they did stuff with Mayo Clinic. Mayo Clinic gave them a bunch of training data, and they built this thing called CTAKES. It is a bear to set up, I don't like UEMA at all, but things work with it. And that sucks because I want something better. Also, I'm very partial to Python. But I would look at, how many diseases are in this data set? How are things relating to one another? Are there any co-references? So that's when it gets very subject specific. That's when we're going back to the subject matter expert of what else can I find out from you? So those are just some other takeaways. This isn't going to fix all. I remember one day I finished a notebook on EDA. I pressed play. It all finished. I had pretty pictures, and someone came to me and said, "Cool, what'd you learn?" I was like, "Nothing." I looked at all these pictures, and they're so cool. Look at these pictures. He's like, "What are you going to tell the client? What are you going to ask them? What have you come up with that we even took this sample of data for?" So while EDA can be very fun and it can produce some really cool pictures, especially those word clouds, be sure and have a purpose, and be sure and think about, what's the next step? How am I going to get to the next step? How is this topic model going to get me to the next step to talking and providing success for a client? All right. Got one thing for y'all. Here's your gift. I need to change one thing in it because it broke earlier, but can y'all see that? Do I need to make it bigger? You get a whole bunch of library imports. All right. So I went ahead and just did some EDA on some random data set. I grabbed all of Harry Potter and just wanted to see what would come out. And we can just take a real quick look at this. I'm just loading data. Because I really like just pressing play on everything, I try and set my constants up here. You notice I only have two constants. I have what's the column that has text. Here, let me make it bigger, just so y'all know what I really mean. Okay, so I've got this Harry Potter data. I've only set two constants. The text column that I'm going to be inspecting, so that's where all the meat is. I want to make some plots, and I want to use this palette, because, I don't know, it looks cool. First things I'm going to do, I'm going to look and see if there's any nulls or any duplicates, and I'm going to drop them. So I see that 1,099 duplicates were dropped. I think these were the lines that said chapter 1 or chapter 2 or something about that, or Harry says, all that cool stuff. Like I said, I like to read the data before I can really get into something. So actually, let me, oh, this is dangerous. It's a live demo. Is it going to work? My imports are still importing. Man, that's a long import. There we go. All right, there's my data. Phew, we made it past that. All right, so we're dropping nans. All right. I like to be really cute in notebooks and make like iPie widgets and stuff to make my life a bit easier instead of just constantly going and getting a new sample. So with just a simple next button, I can go through some samples. The data is not too long, but I'm able to just read some of this stuff and just kind of get an idea of what's going on. I'm just reading data and taking notes. So I'm looking for misspellings. I'm looking for words that I've never heard of or seen before, and that's about it. So for this, I only grabbed sentences. Probably would have been good if I just grabbed paragraphs, but y'all can find your own data. All right. So after that, this is where I was talking about we're transforming things into those feature vectors. I'm using two things. Well, I'm using one thing, and I'm showing you the difference. There's a count vectorizer, where this is just a token is going to be something that is one character or more, and lowercase is false. So we are getting the raw data. It is everything except for like boundaries, like periods, and so forth. And I did this so I could show you all the difference of when I get rid of stop words, when I strip accents. So like Spanish, other language things. I can't think of them. Lowercase, we're going to lowercase all of our data. We upped our token pattern to grab things of 3 characters or more. So that trims out words like I, am, to, stuff like that. But something to be aware of this is when we're doing these token patterns, when we're getting rid of words that are so characters long, we need to read some of that data and make sure there's no acronyms, there's no features that really would help us out that we just threw out the door without even really looking. So beware of that. And then a token has to show up 10 times to be considered. And the top 5% of the words are thrown out. And so just by doing that, we have 26,000 documents of, if I didn't do any pre-processing, our feature set is 17,000 features wide. That's so large. But after doing simple pre-processing, I didn't really break a sweat doing any of this. And we've trimmed it down by almost 15,000 features. That's pretty cool. That's a lot of noise. Maybe I missed some things. I don't know. We'll find it out later. So what's this look like now? So as we saw on that slide, now we have all of our features and their counts. But here we see there's a lot of zeros. That's the problem with text data, is that it's very sparse. Not every document that we're looking at has all of these words. And so we still have quite a bit of noise, so there requires some even more review. So I've got some notes. You can look at those later. What does machine learning see that, let's say we take all the non-negatives for some sample. Did I believe that Voldemort was gone forever? We all only have believed, did, gone, Voldemort. And out of this, notice something else. There's no word order. We've lost all word order. So this is what people say, bag of words. This is just, we're looking at feature counts. That's about it. There's some things we can do to give order, such as engrams. We can do single to bi to tri to quad to, and we can just keep going. And it'll continue to increase our feature space, but it also might be helpful if word order seems important for our task. There's other things such as word embeddings, all that jazz. Read about them. They're wonderful. Distributions, those box and whiskers. We're looking at document lengths. Are y'all just thinking about the cats right now? This is such a cute picture. Anyway, so we see that there's quite a bit of outliers here. While most of our distribution of documents are about 7 tokens long. That's kind of weird. So I wonder what those look like. We can also look at 25 most common features or 25 least common features, or you can slice it however you want and just get an idea of what's happening a lot. There's that word cloud. Isn't that so dope? All right. So now, again, these are coming to questions. Did we come up to any observations? Are these common? Are these rare? You name it. Become the subject matter expert. Try and learn a bit of these patterns. Again, we can read with that next button. If I just ran this, it would show us the outliers, and we could read what are the longer documents. Topic modeling. Here are all just great notes that I stole from someone else on topic modeling. How can we really take control of the topics that are being assigned to words and to documents and so forth? And so, has anyone done most of this stuff? Like, anyone here do like topic modeling? Played around with the kings of it back there. Have y'all heard of PyLDA Viz? That's been so popular lately. At the data science, NTC data science show and tell night, they showed a lot of cool stuff, and I had never used PyLDA Viz before, and it seemed like a really cool tool, so I showed it tonight. Something I forgot about, though, is in topic modeling, we have to choose how many topics there are. And so there are a couple ways to do that, and I left you some great notes on how to do that with these LO curves and finding the highest coherence within this data set. So this is to help us choose our topics. And then once we've chosen our topics, like here, I chose 10 because I disagreed that 2 was how many topics there really was. But you're the professional. You make it happen. So out of that, we're given our topics, our top words with their top probability towards that topic, and how much these words show up in a document that can control what the topic of the document will end up being. So finally, here's even more. Oh, it's such good stuff. Here's the PyLDA viz. So in here, we're able to look at what features are showing up in each topic. Furthermore, what topics are kind of overlapping. So here we see hairy shows up in a lot of topics. Seeing the things that grow and shrink. Asked. That sounds like a word that shouldn't be in there, so we might need to update our stop words list because that controls a lot of topic 4. So these are things that just, we can click around and get to know what kind of data is controlling these topics. What kind of recommendation system would be coming in and saying, hey, we think you'd like this because it had the word science and LDA and data and donuts and all that jazz because of what I've read in the past. And then finally, this is the thing that broke my notebook. This TSNE. I explained a bit of it earlier, but definitely take a sample. Don't try and do what I did and run it on 30,000 data points because that will bog down your browser when it's trying to render it, and then it will break Chrome, and then Chrome takes up all of your RAM anyways, and so it shuts down everything. So I don't have a plot for that, but it basically looks like this. And with bokeh, you can hover, and with that hover tool, you can read those data points and see what text is showing up close together. So that's really what I like, is just that interactiveness. If y'all ever mess with TensorBoard, it's a bit tedious to set up, but TensorBoard's TSNE and PCA visualization tool is awesome. I really like it. So if y'all ever get some time, I'd say play around with that. All right. Thank y'all so much for listening to me. That's all I got for tonight. Are there any questions? Yeah.
How do you handle duplicate valued columns?
Duplicate
So-
valued columns.
So surely in your future vector, there are some words, especially if you want hot code, that show up the same amount of times in the same documents or duplicate in terms of information.
So like the word donut,
Yeah.
if that shows up multiple times?
Like so somewhat random, right? The word donut, maybe the word alligator showed up
Yeah.
in the same set of documents.
Yep.
And didn't show up in the other ones.
Right.
So in terms of machine learning, is duplicative information. But
Yeah, so there's-
distinct words.
Yeah. Let me go back over to this. There's my info on coherence. So when we're going up to these feature vectors, so here's document 0, document 1, down to document 4. We can look at all, 26,000, 29,000 documents that we have here. Earlier in the set, I went ahead and was kind of cheap and just did duplicate removal here. So that's saying if there are just straight up string comparison duplicates, like we haven't put them into the feature vectors, go ahead and remove them. But in some cases, stats wise, sometimes we do see duplicates, and that's representative. So then that comes to the question of modeling of, it's representative, do I keep this? Is this going to show up more? Are these features that are coming in more often than if we remove the duplicates? Is that okay? Because they're going to definitely have a bit more say-so than some of the other features that aren't with the duplicated data. So that's really just a question of how does this affect my modeling? Does that answer your question?
Yeah, to some extent, yeah.
Okay, sorry.
I was going to throw a comment in.
Yeah.
So what Josh said earlier about reading the data, like in text data, that's super important. So if you have features that, you know, the same word that end up being the same across the documents, you gotta figure out why. I mean, it could be coincidence, which isn't that likely, or it could be that, you know, like you said at the very beginning, they just occur in all the documents, almost all the documents. Or actually, a very common case is you find, for example, like new and York would co-occur in the same documents almost all the time, and you realize, well, maybe I should treat that as a phrase instead of the separate words. So it's just that's the kind of digging in and figuring out what's going on with your data.
Thanks. Kevin?
I have a question. Is the feature the same as a data attribute? Is it the same thing or something else?
I've never used the word data attribute. I don't think I have. When I think of a feature, so if we look down here, these are our features. And so because I used unigrams, our features are just every single word. So yeah, when I think about data attribute, I would say yes, that's a feature. Yeah. Jason?
Can you just comment a little bit on data cleanliness? Because I mean, you had mentioned you're using specialized vocabulary for your data.
Right.
I mean, if I try to use UMLS, it's just going to fall on its face.
Yeah. Yeah. So on data cleanliness.
Like you had mentioned misspelling.
Right. Yeah. It's really coming down to it's two things that I've found a lot of misspellings. I once worked with a client that OCR'd their data. So they had scans and they had an algorithm use computer vision, pull out each character, and it did not do a good job. And I think that's the project where I was looking at patterns in subword features, so in the characters. So I wasn't looking at full tokens, it was just within. That came from one, sitting with them and reading the data with them. And one of my first questions is there anything you want me to know right now about this data? Sometimes there are data scientists with me, they're like, oh yeah, I've been through this data, check this out. But sometimes I've worked with some doctors that are like, it just seems like medical data to me. So it's like, all right, making my life harder. So on the topic of data cleanliness, please do make sure and just read 100 to 500 of these documents. Get a random sample, really kind of sit in that data. That's a lot of what EDA is. It's sitting, it's getting comfortable with this data and poking things, seeing if they break or not. So, but there definitely is, do I drop duplicates? Are there words that are misspelled? Earlier I showed this, the 25 most common features or 25 least common. So I did a filter on words had to show up more than 10 times, or 10 times or more. Sometimes when I don't do that, and I do this least common, there is so much junk. And if you just do a keyword search of where that junk is, then you might be surprised you might just straight up find a document that is nothing but zeros and number signs and special characters, and it's a mess. And then when you start looking more for those, I've found plethoras of those. So do you want to add anything to that, Jason?
I guess I would just ask, so if you're looking at healthcare data, maybe the word hypertension is misspelled.
Yeah.
How do you, even if the end approach something like that?
Yeah.
It's important, you don't necessarily throw it at misspelling.
Yeah. Yeah, that's a great point. Yeah, so if there is a misspelling, is that misspelling as common as the correct spelling? Does that just need to become its own feature? Should we look for that and have our own rules-based spell checker? So it's we know this feature shows up a lot. We don't want it to be a separate feature because this is a very important feature. So let's correct it, and now it's included with that other feature in our vector. Another way is this is like heavy weightlifting, but not so much because we have the technology as building a language model. This language model needs to be built on clean data. And what a language model is doing is, given a seed of characters, it's going to take off and say the next characters that it thinks is next characters that are grammar. And so we can then compare what the language model came out with for the word versus what the actual word is. And if the probability of this language model is way higher of being right, then we choose that spelling.
Isn't there a way to do unsupervised synonyms or something like that?
I think so. I haven't really gotten to do much of that. Were you about to say something?
Well, with word embeddings, you do something like TSNE.
Yeah.
Cluster together.
Yeah, so word embeddings, like Word2Vec, fast text, you name it, everything embedding, dealing with words, glove, all that jazz. They've been trained on humongous corpora. And with that corpora, these words that, the quote that came out with the Word2Vec papers, words that show up together, often kind of embed together, or and kind of means somewhat of the same stuff. That is really not verbatim what the quote is. That is way better than what I said, but I hope you get what I mean. But so let's say I train a model here. This is a good point. All these words, when we get into modeling, when we're building a machine learning model, we have our training set, we have our validation set, and we have our test set. Throw the test set away for now. We're just going to look at this what I call the development set. It's our training and validation. And training is what that data is what we're going to vectorize. That feature set is now never going to change. So that's when we're using this. So if, let's say, the validation set, it might have some words that aren't going to make it when we're training, or even when we're evaluating, when it's being transformed into this vector representation, because we only know these words. So when I think of my model as a student, I'm training it with its homework and quizzes, I'm giving it the answers, and now this validation set, I would say, are kind of like some tests. They eventually get their answers back and they can learn from that, which later maybe I need to train on the whole dev set because my training set, the model didn't generalize well to my validation set. So all that to say is our words end up being limited when we're going this route. When we go the route of embeddings and we train on this humongous corpus or even corpora, we have words that are now embedding in this space together. So words like happy, synonym of happy, I guess I can't think of it. Joyful, all this jazz where, let's say joyful wasn't in any of these, but we knew the word happy. Well, now that document is going to lose that happy thought because it doesn't know the word joyful. But if we use embeddings, it embeds in a similar space, and it's kind of like, oh yeah, that word kind of sounds like this other word that I know. So that can give us some synonyms. Stephen?
Do you ever find that there's useful information by looking at like parts of speech tagging or syntactic structure?
I am very interested in syntactic structure, like grouping parent with children and just doing like an underscore to make them a feature, kind of like hard code a feature in here. I haven't done much with that with our models because what we've done has worked and it's worked well. So we try not to over-engineer these solutions. But with healthcare, with part-of-speech tagging, I haven't had much experience. Jason, do you?
Doesn't work as well.
Yeah. Yeah.
It's
Any?
very sparse. So that sparsity basically means that for classification, you don't actually need that sparsity. Right? You get the same result better without it.
There might not be any syntactic structure in those documents.
That's yeah.
The other thing I have to think about is syntactic structure is still messy and noisy, so you're
that aren't experienced or aren't aware of it, because they're interested in seeing more about it, learning more about natural language processing. See if you know it's something for the future.
Great.
Josh, next month.
All right, see y'all next month. But yeah, and even on that topic, earlier I said there are 3 stages of EDA. If y'all are interested in more, we can make a series of this as well. I guarantee you it won't be as long as this one because we're just looking at class balances, how we can weigh features, feature selection, feature engineering, and then also what it looks like if a unseen data set. I just really like this picture. If our model will generalize well to it. So, yeah, Reed.
Question about your use case with the cancer
Yeah.
diagnoses. Did the external features play a significant role? So, did you model on, let's say, different pathologists or hospitals?
Yes, we did. So a lot of our data was across multiple facilities. And so that was part of our EDA of how different is the nomenclature, how different is the language, excuse me, across these different facilities. We found they were very similar. So we didn't have to worry about much feature engineering per facility. We definitely do, given a data set, we might have a doctor's no run inning, if they were the pitcher. And they're just finding cancer everywhere. They're the best doctor in the world. And now a highly correlated feature to cancer could be this doctor's name. So then that goes with feature engineering. Let's make sure that this isn't in there because it's someone's name. That can't be right.
So let's basically stop here and say if you have questions, please come and see Josh afterwards. But I want to say thank you for bringing the presentation to a new level. Thank you.
Thank you all.